Hello, welcome to our final lecture of the semester. We're looking at Chapter 17, or Module 17, Building a Small Network. And at the end of this, well, not at the end of this, after I'm done this video, I'm going to get your lab test sign-up sheet up. So it's going to be an announcement in eCentennial with the time slots and pods. Next week in the lab, or I guess this week in the lab, I should say. Let me know what time slot you want. I'll put your name in. And anything that's not assigned when it comes to test day is fair game. First come, first serve. Yeah, that's kind of how it's going to go. For those of you who weren't in the lab this week or last week, the lab test will be spread out over the final 2 weeks of the semester. So I'm going to split your class, your 2-hour class, into 2 batches of 45 minutes each over 2 weeks. That will allow us to get everybody through. Your final, your theory test at the end in week 14 is going to be available online Monday to Friday. It's going to cover everything over the semester, all multiple choice. I think it's like 30 questions. Just do it. It's like the quizzes you've been doing, just longer. So, with all that in mind, let's look at Chapter 17. Here's everything we're going to look at. We're going to look at the types of devices, different applications and protocols you use, how to scale, which means as networks grow, right? As small networks they grow and become bigger networks and bigger. That's known as scaling. Testing connectivity with ping and trace route, finding out information using different commands in iOS and different hosts, Linux and Windows, and troubleshooting. So let's get underway. So most businesses are small, and most of the business networks are also small, right? Small network designs are usually very simple. They might have a single WAN connection provided by a DSL or an Ethernet connection. They may not have a large IT department. They might actually only have one person who's the entire IT department. He's just the IT guy. Larger networks require a lot more work, right? They require a full IT department and a security department, or a subset of the IT department is the security team to maintain and secure and troubleshoot things and protect your data. Small networks could be managed by a small team, very small team, or one person. Could also be contracted out, and can be a lot of times. Now, when you're selecting your devices to design a network, you have to plan for what you need, right? In terms of use cases and the number of users you have and the types of data that are flowing through your network, the types of bandwidth that you're going to require, and also the budget, right? So you have to think about your intermediary devices, because that tends to be the first things you think about, your routers and your switches, right? How many do you need? How many departments are you going to have? What does the organization look like? And when you're selecting these, you have to think about cost first and foremost, because everything has to come within the company's planned budget, or it's not going to happen. You have to think about the speed and the types of interfaces you're going to need to support the configuration that you want. Now, are you going to add in a bunch of additional redundancy with Ether channel and HSRP with multiple routers, which are things you're going to learn about in later semesters? If you can, then yes, right? But if not, right, if you don't have the money for the additional devices to do those things, then it's not going to happen. You have to look at how quickly the network can be expanded, or not even necessarily quickly, but how it can be expanded over time. And what services does the organization require? What operating systems are suitable to provide these features and services? When it comes to IP addressing scheme, you're going to have to, if you're designing a network, you have to create and use one. That will allow for all the hosts and devices to have a unique address. And we're not even talking about type of IP, I'll get to that in a second. But this has to cover your end devices with a variety of different connections and types: wired, wireless, remote access, servers, printers, security cameras, intermediary devices like switches, routers, access points. And you should plan and document and maintain this scheme as it grows over time. If you do this properly, it makes your troubleshooting a lot easier. Also, if you're designing a new network, you're probably going to want to consider in configuring dual stack, which is both IPv4 and IPv6 running in the same organization. While we are migrating and should be migrating to IPv6, a lot of stuff still runs in IPv4. To provide reliability in a network, and also to provide faster throughput, you need redundancy. Redundancy helps you eliminate your single points of failure. So you can do things by installing duplicate equipment for anything that's critical, and configuring them in a full mesh or even partial mesh topology. This is a full mesh topology right here, right? Every device is connected to every other device. So we've got 3 servers here. They're available in case of failure, and multiple links to each switch with 2 routers in here, right? Lots of redundancy here. Now you might even have your redundant servers do things like load balancing, so the traffic is distributed across all the servers and they're active, and that's a very, very common thing. You have to manage traffic properly, right? So you're going to want to enable quality of service, implement quality of service rules within your network to prioritize higher priority traffic, such as VoIP. If you have VoIP in your network, we've talked about this previously, I believe. VoIP requires very low latency, so it has to be very high priority traffic. And if you have VoIP in your network, you have to design the whole network around it. Most networks these days do have VoIP. Other things like email, instant messaging, transferring files, they can be lower priority. And you can have, with priority queuing with quality of service, you've got 4 queues: high, medium, normal, and low. And traffic in any of those queues will jump priority when it's received by that device. So if you've got a bunch of instant messaging traffic coming through, VoIP traffic is received, that's going to be sent out the router before everything else. So it's something you tend to configure. Now we're going to look at some common applications and protocols. Once you've set your network up, you still have to have different applications and protocols for it to work, right? We're not just connecting devices for no reason. We're connecting devices and people so they can do a job. You've got 2 forms of different software programs or processes that you're going to have. You're going to have network applications. So these implement application layer protocols and are able to communicate with the lower layers of the TCP/IP stack. And application services. So these are for applications that aren't network aware, right? Or other applications that aren't network aware. The program that that interfaces with the network and prepares the data for transfer, that's an application layer service. So some common network protocols that you have in a network to support applications and services used by employees. For remote access, Network admins commonly use SSH or Telnet, probably SSH though, because SSH is encrypted end to end and Telnet is not. Telnet is okay for connections like literally across the room, but that's about it. HTTP and HTTPS. S missing on the slide here. Should be an S there. For connecting to a website in a browser, right? And interacting with the company. SMTP, POP3, and IMAP for email. Now the main difference between so SMTP is your between mail servers communication. POP3 or IMAP are used by clients to retrieve email, and more commonly you see IMAP these days. POP3 is an older protocol, and it when you connect to the server, it downloads everything. Whereas with IMAP, you just get the email headers, and when you click on an email in your inbox, then it pulls down the body. That's why you tend to see IMAP. It's better for mobile. SFTP, security, should be secure file transfer protocol. You might see FTP, but more commonly SFTP to upload files between a client and an FTP server. This is commonly used by developers, web developers, to access a website, a web server rather, and upload their files to the web server from their local development machine. DHCP, you've seen this commonly, or you see this commonly for acquiring IP addresses. You've got a DHCP server, and clients' devices acquire their addresses from the server. And of course, DNS. I've mentioned this one before. It's the building block to the internet, right? Without DNS, the internet wouldn't work. It maps domain names to IP addresses. And you don't necessarily have to have a single server for any one of these, right? You could have multiple network services on one server. Additionally, you could have multiple servers for some of these as well. Like if you've got the budget, you might want more than one web server with a load balancer in front of it. So if one server goes down, your website's still up. It's a common practice. Now, all of these services require protocols to work. Protocols define the processes on either end of the communication, the types of messages and the syntax of the messages that are sent, the meaning of the information fields, and how they're sent, and the expected response, and how they interact with the lower layers. So we're talking about pieces of encapsulation and decapsulation here, right? Elements of that, but not the whole process. Usually you tend to use the secure versions of protocols wherever possible. So, for example, HTTPS, SSH over Telnet I already mentioned, SFTP over FTP again, because you want encryption, right? That's what the secure part gives you. It gives you encryption end to end. Video and voice, VoIP, have become extremely common, increasingly more popular over the last 5 to 10 years. In fact, they're very common now, right? You have to have the correct equipment installed on the network to support these. You have to enable quality of service. If you have VoIP, we've mentioned the whole network needs to be designed around that, and you have to have infrastructure that supports it. So, things to consider. Now, as you scale up, as your network grows, which is a common thing, this happens, right? It's a natural process for many businesses. As the business gets bigger, the network gets bigger. We add more people to a department, we need more devices for them to work off of, or we add more departments to the company. Maybe we start off, I say we, I'm saying we, but I mean like the business, right? Maybe they start off outsourcing their website, and then they decide to bring it in-house and build their own web server and infrastructure and stuff. So this happens. To scale a network properly, you have to have proper network documentation of both the physical and logical topology. So, and make adjustments to this over time, right? As the network changes, you change the diagrams accordingly. You're going to want a complete device inventory, a list of all the devices that are in the network, so you know what is where. And also, as you're growing the network, you may want to replace some of the older equipment if it's approaching end of life. You have to have a budget, right? An itemized budget that outlines what needs to be spent, upgraded when, and how much it's going to cost, and does the budget allocate for it, right? It has to be, that's all part of the process. And you're probably going to want to do some kind of traffic analysis on a continual basis, right? To see what your network usage is actually looking like. Because you might see things when you analyze your network traffic in the ways that the network is being used that differ from maybe the intended usage or design, right? Maybe VoIP is more common than you thought it might be, or something like that. So you have to take all of these things into consideration to make the decisions in how to scale the network. What is the best capacity, and what is the best way we can grow the network to support the continued growth of the business. Protocol analysis, there's a bunch of different network management tools that you can use to do this. They can analyze the flow of network, capturing traffic during peak utilization times to identify the different types. You can perform network captures on different network segments and devices, because some traffic might be unique to particular segments. You can evaluate the information that's gathered by a protocol analyzer based on the source and destination of the traffic, as well as the type that's being sent. And then you can look at this and use that information to make decisions on how to better improve the network, and how to maybe just manage the traffic better to boost your efficiency with your existing network equipment. You may have many operating systems in an organization, and all of them provide built-in tools to give you network utilization information, like things like the current OS and its version, the CPU, RAM, and drive utilization, any non-network applications, and your network applications, right? What applications are using your network, and how much of it, and in what way. It's important stuff. So you're going to analyze all of those. So for verifying connectivity, regardless of the size of the network, and regardless of what operating system you're using, you're going to need to do this at some point to verify for troubleshooting purposes, for testing purposes, if you've just configured something for verification purposes, right? So ping is something we've used all semester, right? Ping with an IP address tells you whether it's up or not. Ping with an FQDN, a fully qualified domain name, does the same thing. If the ping with the FQDN fails, but the ping with the IP succeeds, that tells you if your DNS is working or not, right? So all of these things can be used to tell you what's going on and help troubleshoot problems. In Windows, you can, if you issue a ping, you'll see one of three indicators. If it's an exclamation mark, it's successful. If it's a dot, it means that the time expired waiting for the reply, so it could be a timeout. And if it's a U, an uppercase U, that means that the router replied with destination unreachable. So it usually indicates a routing table issue. You can go and verify. Usually you follow that up with a trace route to see where the packets are failing, and then go into that particular device and verify its connectivity. And you'll find that something's wrong, right? Either an interface is down, a route wasn't installed correctly, or something else is going on. Maybe a cable's just unplugged. Within iOS, you can also use an extended ping. This works in privileged exec mode, and then you just type ping without an IP address, and you get an extended ping. And you can customize some of the elements before you send it. It's a useful thing, and if you want to do an IPv6 extended ping, you just type ping IPv6, and you'll get that. Ping is great for telling you if there's an issue or not, but not great for telling you where the issue is, right? Traceroute is your tool for once you've detected that there's an issue, troubleshooting where that issue is, and narrowing down the source of the problem. The syntax for traceroute varies a little bit between different operating systems. In Windows, it's trace RT. In Cisco and Linux, it's traceroute spelled out. The nice thing about traceroute is it will show you each hop, each router that packet passes through between source and destination, plus the source and the destination. It's pretty great. It's pretty great. Oh, plus the source, plus the default gateway of the source, right? So if you've got this example here, this topology, and you ping from PCA to PCB, and it fails, well, that just tells you the packets didn't get through, right? It doesn't tell you why. You could perform a trace route and find out, okay, it's getting to router 3, and then it's failing. That means there's an issue on router 3. You need to go look at that. To interrupt a trace route, you just hold down Control and C. We've used this in the lab, right? And you're totally going to use this next week on your practical. Or next week. Yeah, it could be next week. Or the week after, in the next 2 weeks on your practical. So there's an example of a trace route in Windows. Just Control C to interrupt it. And there's an example. Oh, let's look at that. So we see request timeout here, so we know our packets are getting to the default gateway and then failing. So that indicates there's an issue between router 1 and router 2. Here's an example of traceroute in Cisco iOS on a router. So we've gone into router 1 and we've tried to do a traceroute. This is the traceroute succeeding. Here, the same thing but failing. If you want to interrupt it, instead of Control C, you hold down Control Shift and 6. And technically they work a little bit differently, but they provide you the same information. You can do an extended traceroute as well. It provides for a whole bunch of additional parameters. You can force it with IPv4 or IPv6, for example. All kinds of useful stuff. Same thing with Cisco's iOS. To issue an extended traceroute, you just type traceroute with no destination. Now, one of the most common tools you can use for monitoring and troubleshooting is establishing a baseline. A baseline is just the results from your average like peak performance workload on your devices, right? So you perform a baseline to get an idea on what the flow of traffic's like, and then you can use that to test against, right? That's your point of reference for any additional testing and troubleshooting you do after that. You can even use professional grade tools for this. They're pretty useful. But ping and traceroute, honestly, I use them all the time. All the time. Super useful for troubleshooting network issues. Now, when it gets into hosts and iOS commands, one of the first things you tend to do is verify IP configuration, right? With Windows, that's going to be the IP config command, possibly with the /all option, which will show you some additional information. If you want to release and renew your IP from a DHCP server, then you can do that using IP config /release to release the IP, and then IP config /renew to send out a new DHCP request and pull a new IP. You may also want to look at your DNS cache. So you can do that with IP config /display DNS. And if you want to clear your DNS cache locally, IP config /flush DNS will do that. That's not in the slides. In Linux, pretty much everything you do with IP config, you can do with ifconfig, which is an older command, or more commonly IP address, which is a newer command that is replacing ifconfig. Ifconfig is deprecated. It's a very old command. It still works in some distributions, but it's in the process of being deprecated. So here we see ifconfig. We see our IP addresses. Basically the same information you see with ipconfig, right? In Mac OS, it's a little bit different. So you could use ifconfig in Mac OS as well, but you could also use network setup, list all services, and network setup get info. And we see some information there. ARP. So if we're looking at your ARP table, we'll show you. You recall ARP is your mappings of IP addresses to MAC addresses, your logical addresses to your physical addresses. So you can look at this, see if anything looks funny, flush it. It's a common thing to do. Delete your ARP cache, especially if there's been an ARP poisoning attack. You want to clear your ARP cache just to be safe. Common things you tend to use, the show commands, right? In Cisco, show running config will show you the running configuration. Show interface or show interfaces will give you the status and display any error message. Show IP interface will give you the layer 3 information. I've commonly used show IP interface brief in the lab, and you have too, right? I showed you that. Show ARP looks at the ARP table. Show IP route looks at the routing table. If for the IP commands, if you want version 6 information, just replace IP with IPv6. Show protocols will show you what protocols are operational, and show version gives you a bunch of information about what's going on with the device, including its memory and interfaces. Next up we have CDP. So CDP is a Cisco Discovery Protocol. You can use show CDP neighbors to find out information about neighboring Cisco devices. It'll give you information such as the device identifier, if it's got a host name configured, its list of IP addresses, what ports they're connected on, what capabilities they have, and whether it's a layer 2 or device or a layer 3 device, a layer 2 switch or a layer 3 switch, or a router, and what the hardware platform is. And all of this information is one of the reasons that when you're securing a network, you tend to disable CDP. Because, I mean, if you can find this information, yeah, it's great for troubleshooting, but an attacker can find the information too. I talked about show IP interface brief. Here it is. So it gives you more detailed, well, more specific information. Brief, summary information, right? So we see we've got two interfaces. Um, their IPs, their status, so they are administratively up. You've issued the no shutdown command, and the line protocol indicates that the device on the other end is connected and it's on and been configured. So this will indicate there's a cabling problem if it's down and you expect it to be up. This will indicate, it could just be a faulty cable. This will indicate that you forgot to issue the no shutdown command, or it's accidentally been brought into a down status. We're not looking at a video. We're not looking at a video. Troubleshooting. There's all kinds of different troubleshooting methodologies. There's a couple on the slides. I'm not really going to go through them a great deal because I just use a different way, right? And everybody does. But identifying the problem is the first step of the process. And honestly, it's sometimes the hardest step. Something weird's going on. You got to figure out why. So that's where you got to use your tools at your disposal. Ping, traceroute, your show commands, right? Depending on where the problem is and what the problem is. In this, you're going to try to figure out what the problem could be and eliminate what the problem isn't. And once you've figured out what the problem is, how do you fix it, right? It could be you've got a bad interface on a router or a switch. You got to replace the interface. How long is that going to take? Is there another interface on that device that you can just move that configuration to in the time being and replace it later? Or do you even have another router kicking around? Probably not. Just one example. Also documenting what happened and how you found it and what was done to fix it could be useful for you or any future people who come along behind you, any other people on the IT team, to figure out stuff. It's useful. In some places, you may not be able to resolve the problem immediately, like you need to replace some equipment or something, so you have to escalate it somehow, and that's going to be in the company policies as to how to do that, right? In Cisco iOS, you can use the debug command if you're really stuck in troubleshooting. It's a useful thing. It's entered in privileged exec mode. There's actually a bunch of debug commands, and you could use debug ? Right, to show you how it could be completed. When you're done with it, you can type no debug, or you can type undebug. No debug all, undebug all, both work. So here's what it looks like. Turned on debugging, and we see all of our messages. There's going to be a whole bunch of debugging information about what's going on the device written on the screen continually. It's a useful thing. I want to make a note about, though, not necessarily on remote connections, though, but if you're connected directly to the console port, you're going to see these. Common issues that you might run across. Cabling issues. Before we get into duplex and mismatch issues, broken cables. Just throwing it out there. It's a thing that happens. If you're having issues and everything else looks right, try replacing the cable with another cable that you know works. It might fix it, and then you know that cable's bad. You can set it aside to analyze later, or just throw it away. Do whatever you're doing with your broken cables, right? If it's something wrong with the ends of the cable, you can probably just make the cable a bit shorter and make a useful cable out of it that's a bit shorter, right? Outside of that, Ethernet interfaces have to be the same speed in duplex. So if you've statically set the duplex on one end to be either full duplex or half duplex, and the other end is expecting the other of those, you're going to get a duplex mismatch. And then the link performance will be very poor, or might not work at all. Usually I just leave the auto negotiation on, because it fixes any of these problems, right? These might be difficult to troubleshoot because you might get communication still occurring. IP address issues. Maybe you assigned the wrong IP address. So show IP interface brief helps indicate what's going on. Or maybe you're pulling an IP address from a DHCP server and you get one of these APIPA addresses instead, a 169.254.something.something. That indicates that your device didn't pull an IP from DHCP, so you can't communicate with the DHCP server. How you go about troubleshooting this once you know that's the problem? You could do a variety of different things, including just set a static IP in the subnet that you're expecting to get an IP from with the proper default gateway and see if you can ping the server. If it can't, you know you got a problem, right? One of the most common problems you have is your default gateway. Your default gateway is the router that you're directly connected to, right? Could be through a switch, but it's still the router. If you don't have the correct default gateway set, or there's no default gateway set, you can't get outside of your local network. Also, if the default gateway goes down, you can't get outside of the local network, right? So this is where you use ipconfig to verify that you've got the correct one, show IP route, and show IP interface brief on the router to verify that the output from ipconfig and show IP interface brief matches, and ping and traceroute, right? Honestly, one of the most common things I do when there's a network issue. Can I ping my default gateway, yes or no? Because that'll immediately tell you if that's the problem or not. And if that's the problem, there's no point looking anywhere else. Go fix it. That's where you check, go into the router itself, check to make sure it's on and the interface is in an up status. Check to make sure it's got the correct IP address. Check the cabling. Maybe the cabling's broken. Maybe something got unplugged. Who knows? DNS issues happens all the time too. For DNS issues, really to figure out whether I've got a DNS issue or not, I try to ping my default gateway. And this is with any network issue. If that works, I try to ping externally by IP address. For these, it's useful to remember 8.8.8.8 and 8.8.4.4. They're two publicly accessible DNS servers provided by Google that anybody can use internally in their own network. So if you're a Rogers customer, you might want to consider using those in your network. Just set those on your router, and then Rogers DNS won't affect you ever again. But if you can ping externally by IP and you can't ping by fully qualified domain name, you know your DNS is an issue. So that's what you got to fix. You could switch your DNS to Google's. You could talk to your ISP and say, hey, there's a problem. It's totally up to you at that point. But fixing it without switching to Google, you got to escalate it. There's no lab. There's none of that. So what did we learn? There is a lab this week, right? But what did we learn? We learned a lot of stuff about building a small network. We learned about redundancy. We learned about scaling a network. We learned about testing and troubleshooting a network. We learned a lot of stuff. So, I'm just going to skip through those last slides at the end as I tend to do. Right? What did we learn? We learned a lot of stuff. Most importantly, this week, sign up for your practical test. Your practical test is going to be in class, in person, in weeks 13 and 14. If you don't sign up for a slot this week in the lab, then, and you're just going to come up and tell me what pod you want at what time, and I'll put you in. If you don't do that this week, first come, first serve. You'll see what's available because it will be available as an announcement in eCentennial. And you should see it probably by the time you're watching this video because I'm going to do it next. With that in mind, take care, be safe, have a great week. It's been an awesome semester with you guys. This is the final video for the semester. This week and next week and the week after, we are going to have our practical test, and the final week we're going to have our theory test as well. So I look forward to seeing you in the practical test. And actually, I did want to go through, forget the take care, be safe part for now. I did want to go through a quick configuration and subnetting, so let's do that. Alright, so what sort of thing do you need to do for your practical test? We're going to do one quick round of subnetting, and we're going to apply it to configuration, and I'm going to show you the super easy way to apply it to the configuration as well. We're going to take 192.168.0.0/24. We're going to make two subnets out of it. We're going to fill in this table, and then I have a topology set up here. We're going to put subnet 0 here. We're going to put subnet 1 over here with a loopback IP. We're going to use the last usable IP for the router. We're going to use the first usable for the PC. And we're going to ping and trace route it. And if you can do that, that's your practical test, basically. Also, there's a practical test posted. We're going to try to do it this week in class, or I'm going to give you time to do it this week in class. But you should also give that a go in Packet Tracer a few times. Practice before we get to our lab class on Wednesday. And then life will be easier. Or whatever day your lab class is. So, 192.168.0.0/24, two subnets. What's our first step? We need to know what the subnet mask is, right? It's a /24, so that means the first 24 bits of the mask are ones, or network bits, right? So our division between network and host currently is right here. We need two subnets, so we're going to borrow 1 bit, right? 2 to the power of 1 gives us 2. We're going to take that next host bit in sequence and turn it into a network bit. We're going to take that 0 and turn it into a 1. And we get our new mask, right? Which is 255.255.255.128, because we borrowed 1 bit and its value is 128. And that is also our increment. Now we have all the information we need to assign our IPs. Subnet 0, the network ID is going to be our initial reservation, which is 192.168.0.0, and it's now at /25, right? Just tabbing over to make my life easier for later. We're incrementing by 128. We're incrementing in the 4th octet. So the network ID for subnet 1 is going to be 192.168.0.128. And if we increment one more time, we get 256, which we know is not a valid IP. I'm not even sticking the /25 there. But that indicates that it's easier to figure out your broadcast, right? We've been doing a lot of this in the lab. So our broadcasts now are going to be 1 IP less than the next network in sequence. So this is 192.168.0.127. This one's going to be 192.168.0.255. And this one's going to be 192.168.0.1, right? We can think of our network ID and our broadcasts. Whoops. What did I just do? As the boundaries to our subnets, right? So 1 more than the network ID. That's going to be our first usable host to 1 less than our broadcast. It's going to be our last usable host. So we get 192.168.0.126. And down here we get, this is going to be 129. And this one's going to be 192.168.0.254. And we're done, right? If this is your practical test, you just got 50%. Congratulations. You could, in theory, submit your test and walk out the door. I don't recommend it. Now, we're going to configure this topology. But I promised you a different way. We're going to do it the easy way. We're going to write a script. That's why I got a second document here. So So we're going to assign the last usable IP to the router, first usable to the host, and it's just a router we're configuring. So to write a script, you could comment it like this. This is going to be router 1, or you could just say R1. You're just going to type the commands as you would in the command line, but you're going to type them here, and we're just going to copy paste them in. It's going to be great. The nice thing about doing this is if you have multiple devices to configure, you can just copy paste your script, modify those couple things, and paste it right in. If you make a complete mistake and you want to reset it and start from scratch, you can totally do that. I'm going to use the shortcuts wherever possible. So the things we're going to do: enable, configure terminal, right? You got to do those first, and set the host name. Host name R1. We're going to set our passwords first, I guess. Line VTY. No, we'll do our enable password first. Enable secret class. Line VTY 015. Password Cisco. Login. So that's our privilege exec path, right? I can't spell privilege right now. Enable. Password. This one's going to be our telnet remote access, right? Passwords, which we should set to SSH if we're doing this properly. Console password next. Line console 0 password Cisco login. Let's do our banner message of the day, I guess, next. I think we're going to need an exit here. Banner, MOTD, unauth. Prohibited. I'm doing all this by memory, by the way, so hopefully this all works. And let's enable the password encryption service. And we should be in privileged exec still, so we should be able to say interface gigabit 000, IP address. We're going to give it 192.168.0.126 with our new mask, and bring it up. And our loopback interface, IP address 192.168.0.255 with our new mask, and no shut. Now, let's just scroll for a second because I typed that pretty quick, it seems like. You can pause if you need to because this is a video. I'm going to select all, copy. Moment of truth, did I do this well? Let's find out. Say no, hit enter, paste. Oh. Always scroll for sanity check. Yeah, looks like everything took. We didn't see an error. And show IP interface brief. Let's make that a bit bigger so we see our stuff. Yep, we see loopback didn't take an interface. Or didn't take an IP. Why does that say that's a bad mask? Should be right. Hold on a second. Normally I would pause and troubleshoot this, but that was right? Oh, it should be 254. I put the broadcast in. Oops, my bad. So, I could just go and switch that out, but let's pretend it's a bigger error. Here's what I'm going to do. It should be 254. I'm going to copy it all again. I'm going to reload because we didn't save anything. So we didn't have to erase startup config. And we should get a clean config, and we'll try to paste it in again. I could have just gone and removed or added that IP, right? And it would have taken. That's why I always go through and sanity check. Make sure I didn't miss something. Whoops. There we go. So say no, right? Return to get started. Right click and paste, or just click paste here. And show IP interface brief. There we go. That's a little bit better. So we see our password encryption service. We see our enable secret. Our IPs. Banner message of the day. Our console password. Our line passwords. We're good to go. It worked. Now all it's left to do is give this an IP and ping and traceroute. Make sure it works. Oops, I gotta give it an IP first. So this is going to be 192.168.0.1 with our new mask. And our, whoops, 192.168.0.1. 128. There we go. I think I typed 126. Because I was thinking ahead about our default gateway, which is going to be 126. And if we go into our command prompt now, simulates exactly what you're going to see in Windows. Type an IP config to confirm. We should be able to ping and trace route it. So ping 192.168.0.126. That works. So we should be able to get here. It's the loopback on the router. And do a trace route 192.168.0.254. Boom, we're there. This is going to be one of the required screenshots in your submission, so you might want those as well. And with that, if you have any questions, ask in the lab. We can go over some more. You're going to do that practice. I think you should be fine, honestly, but we can do some more subnetting practice. Don't forget you're allowed a one-page reference sheet. Whatever you want to write on it, all you're limited to is the 6 sides of the paper. With that, take care, be safe, have a great week. Bye for now.